Hello and welcome. In this video, we will continue our exploration of vector calculus, discussing an important property of vector fields called the curl. The curl of a vector field is a measure of the field's tendency to produce rotation about a given point. Throughout this video, you'll probably find it helpful to think of these vector fields as describing the flow of some fluid like water. So let's visualize a vector field, and let's set a point at a specific location in that field. And imagine anchoring a small paddle wheel at this point. The wheel should start to rotate based on how the vector field flows at this point. As you can see, the wheel is rotating counterclockwise. This makes some sense because the flow has a larger magnitude toward the right of the wheel, which overpowers the smaller magnitude flow in the opposing direction at the left of the wheel. The fact that the wheel is rotating indicates that the vector field has non-zero curl at this point. Mathematically, it will be useful to define the curl as a vector quantity, so we need to assign it both a magnitude and a direction somehow. Here's how we'll do it. The direction of the curl vector will be determined by the right-hand rule. If you use your right hand and wrap your fingers in the direction of the rotation, then your thumb will point in the direction of the curl vector. Since the wheel is rotating counterclockwise at this point, the curl vector points upwards. The magnitude of the curl vector will be related to the rate of rotation. Faster rotation will correspond to the curl having a larger magnitude, while slower rotation will correspond to the curl having a smaller magnitude. Let's move the point to another location and observe how the curl vector changes. The curl vector has a larger magnitude at the new location because the field induces a faster rotation at that point. Let's move the point again. Notice that the curl vector still points up, but its magnitude is decreasing, indicating less and less of a tendency to rotate counterclockwise. Now, it's also possible for the field to have zero curl at a point. This means that the field induces no net rotation at that point. Notice that the arrows to the right and left of the wheel have the same magnitude and direction, hence they would produce a net rotation of 0. Let's move the point one more time. Notice that the field in this region causes the wheel to start spinning clockwise. So by the right-hand rule, the curl vector now points downward. Let's practice determining the direction of the curl vector based on a picture. Try to decide what the direction of the curl vector will be at the specified point. Visualize the paddle wheel, and try to decide whether the field will cause it to rotate clockwise or counterclockwise. Then use that information to determine the direction of the curl vector. Go ahead and pause the video while you do this. Since the flow is stronger toward the bottom of the wheel, we should expect it to begin rotating counterclockwise. So by the right-hand rule, the curl vector will point upward out of the screen. Now what about this new point? Which direction should the curl vector point? Pause the video to think about it. We expect the paddle to rotate clockwise this time, since the flow is stronger toward the top, so the curl vector should point downward into the screen. One more. What about the curl vector at this point? You know what to do. Since the flow balances at this point, we expect the paddle to not rotate at all. This indicates zero curl, meaning that the curl vector is in fact the 0 vector. So far we've been dealing with two-dimensional vector fields, but many fields are three-dimensional. How should we define the direction of the curl vector in a three-dimensional setting? For this vector field, there are a lot of ways, infinitely many actually, that we could orient the wheel and still have it rotate. For example, this way, or this way, or this way. Which direction should we choose? The orientation of the paddle obviously changes the rate of rotation. Some orientations produce faster rotations, while others produce slower rotations. The direction of the curl vector will be determined by the orientation of the paddle that produces the fastest counterclockwise rotation and obeys the right-hand rule. We've done a lot so far to build up what the curl is conceptually, but now let's talk about how we would actually compute it. Given a vector field with components f1, f2, and f3, we can compute the curl of the vector field using a determinant, similarly to how we would compute a cross product. You'll notice that the second row consists of the differential operators d by dx, d by dy, and d by dz. This is new and unusual, but let's walk through the calculation to clarify. Just like computing the cross product, we'll cross out the first row and column, then compute the determinant of the resulting matrix. Instead of multiplication, we apply the differential operator, meaning compute the derivative of the function it's acting on. Then we apply the same process again for the first row and second column. And again for the first row and last column. The fact that the calculation closely resembles the cross product is maybe not so surprising, especially given all the talk about the right-hand rule earlier. In fact, because of this similarity, there's another notation that is often used for the curl. Let's write the row of differential operators in vector notation. This object is usually called the del operator. Then the curl is simply computed as del cross f. I want to emphasize that the curl is not the same as the cross product, just that the calculation follows a similar pattern using a determinant. If we are evaluating the curl at a specific point and we want to highlight that, then we may do so using function notation. The curl is of significant importance in physics, especially in the study of electromagnetic fields. And the curl plays a central role in the next of the big integral theorems, Stokes's theorem. This is where we will be headed next. Thanks for watching.